We will focus now on a number of key equations in the course and the concepts associated with them. First is intensity. We have two equations. The emitted intensity refers to the intensity emitted at the surface of a black body. This is the amount of light produced every second in every meter square on the surface of the black body. And this is why we use the radius of the star as the distance to the center of the source. So this is used in the equation sigma T4 in the Stefan-Boltzmann formula. This gives you the intensity of light at the surface emitted by the black body as function of its surface temperature. I received would be the intensity of light received in some region of space after it has traveled away from the source. So this would be your intensity per unit area at a distance r from the source. And you notice that when r equals to the radius of the star, then the two intensities become the same. In either case, when you add up the intensity, when you multiply by the entire surface area of the star, you obtain the luminosity of the star, which is the total light, total radiation, including all the wavelengths, the total radiation emitted per second. This is the same thing as power output. If you multiply the intensity at the distance r, the intensity received, by the surface area of the big sphere here, you also obtain luminosity L. In that sense, the two values of luminosities are equal, whether it is emitted or received. The other part here is apparent luminosity, or lowercase l. Now, this has to do with an observer. If you consider your pupil for the human eye as a circular aperture, or you consider a much wider telescope receiving sunlight, then the apparent luminosity is simply the total amount of light, the total amount of energy from the light received every second. So this is comparable to power, but it is only the total energy in this given area. So if you have an aperture of diameter d, and then that means its surface area is pi times d over 2 squared, and if there is an intensity I incoming on the object, then, and assuming the intensity is normal to the object, if it's incident at an angle, then you'd have to do a cos of theta. So let's assume normal incidence. Then the apparent luminosity would be equal to the surface area of the aperture times the intensity received. So that would be equal to the apparent luminosity, and therefore the intensity would be the apparent luminosity over the surface area. A synonymous to apparent luminosity would be flux. Considering a star with light reaching the Earth, and the light arrives into the Earth with an intensity I, this would be the intensity received, which depends on how far is the star from Earth. Now, if we take a small aperture, say the human eye, then the apparent luminosity will be small for a given intensity. If we have a very large telescope with a much wider diameter, then we expect the luminosity to be much larger. So the apparent luminosity, how bright the object appears to be to a telescope, is much greater than how bright it appears to be to the human eye, to the point where some stars, which are completely invisible to the human eye, will be visible to a larger aperture telescope. So the apparent luminosity is how bright an object appears to you, and it depends on how good is your instrument. The intensity is an objective measurement of energy per unit area. So intensity is for a standard area of 1 meter square. Apparent luminosity is for whatever area you have. Now, the magnitude scale. This is a logarithmic measurement of intensity, or rather a logarithmic measurement of the apparent luminosity of an object, because your brain picks up the light received from a source and your perception of it, so your subjective perception of the brightness, is a logarithmic function of the actual brightness. So if we have two objects that have a relative apparent luminosity L1 and L2, and let's say one is brighter than the other here, then their apparent magnitude will be a logarithmic function of their apparent luminosity. And if we compare the luminosities, so if we subtract the luminosities, then the relationship is a ratio of their luminosities. So when you subtract the magnitudes, their intensities or luminosities are represented by a logarithmic function, at least as far as a ratio is concerned. Well, the idea here, let's say I define the magnitude 1 to be some constant times log of L1, and then magnitude 2 would be some constant times a logarithmic of luminosity 2. When you take the difference, then this becomes logarithmic L1 minus logarithmic L2, and this is a ratio. But then you're thinking the ratio is in reverse order. It should be L1 over L2, not L2 minus over L1. This is because the magnitude scale decreases when you increase the brightness. This scale is inspired by the original magnitude scale that was developed by Hipparchus. It is built in a way that whenever the difference in magnitudes between two stars is 5 points, so let's say M1 is 6 and M2 is 1, so 6 minus 1 is 5, then the ratio in luminosities, in apparent luminosities, would be, well, logarithm, this is logarithm base 10, is 2. Therefore, L2 over L1 is 2 to the 10, or 100. In other words, L2 would be 100 times L1. Whenever the magnitude increases by 5 units, the apparent luminosity decreases by a factor of 100. M1 has a larger magnitude than M2. Star 1 has a larger magnitude than star 2, which means it is fainter by a factor of 100. So if the difference in magnitude is plus 10, this becomes 4. And log of L2 over L1 is 4. So L2 over L1 is 10 to the 4, or 10,000. 100 times 100. So I leave it to you as an exercise to demonstrate that when the difference in magnitude is 1, the ratio of brightness, so the ratio of luminosities or intensities, would be 2.51. Apparent magnitude is a measurement, is a function of the apparent luminosity of an object, how bright it looks to a given instrument. The apparent luminosity of an object depends on two things: how bright is the object, its luminosity, and how far is the object from you, the distance. So two objects that have the same apparent brightness will not necessarily have the same absolute brightness, the same luminosity, if their distances are different. So we need a means to measure stars without this distance factor interfering here. So we need to measure the stars from a common standard distance. How bright would they look if they were placed at the same distance? And the standard distance we use for stars is 10 parsec. So the absolute magnitude of a star, capital M, would be the magnitude of the star if it was at a distance of 10 parsec from you. So a star like the sun, which appears to be very bright because it's so close to us, if you place the sun at 10 parsecs, its absolute magnitude will be roughly plus 5, barely visible to the naked eye. Now, when we compare the absolute magnitude of a star with the absolute magnitude of a different star, we are comparing them side by side. So the difference in magnitude that they have reflect a ratio in not apparent luminosity, but in absolute luminosity. So we would say that the difference in magnitude, in absolute magnitudes between two stars, is a direct function of their ratio, is a logarithmic function of their absolute luminosities ratio, as opposed to apparent luminosity. And we can go one step further and incorporate the distance of a star to its magnitude. So if the apparent magnitude of a star measures its brightness, and it depends on the distance of a star, and then the absolute magnitude of a star measures the brightness of a star irrelevant, and the distance is fixed at a standard value of 10 parsec, then the apparent magnitude of a star minus the absolute magnitude of a star will be the difference, will be the ratio, rather, of apparent luminosity and absolute luminosity. So its apparent luminosity will depend on its intensity. So absolute luminosity, apparent luminosity will depend on the intensity measured at its current distance r, while the absolute luminosity would be its apparent brightness when measured at 10 parsec. So let's define the apparent magnitude to be a measurement of magnitude at a distance r. So that would be associated with the intensity of light at the distance r. The absolute magnitude would be measured at a distance of 10 parsec, therefore corresponds to the intensity of light at 10 parsec. So apparent magnitude minus absolute magnitude, taking this formula, replacing m1 by small m and m2 by big M, would be 2.5 times log of the intensity at 10 parsec. So L2. Now L2 and L1, not the same thing as I, but they are proportional. And of course they depend on the size of the observer. But if they are observed by the same instrument, then this part here will cancel out if you take the ratio, and you will end up with the ratio of intensities. So basically, what we're saying here is that this is the ratio between the intensity at 10 parsec and the intensity at a distance r. And then we know the inverse square law, that the intensity ratio of intensities between two points from a point source at the distance r1 versus distance r2 would be r1 square over r2 square. And here, for 10 parsec is r2, and then r1 is just the unknown distance r. So apparent magnitude minus absolute magnitude would be equal 2.5 log of intensity at 10 parsec, which is 1 over 10 parsec square, and then over intensity at distance r, 1 over r square, like this. So inverse. Square we factor out from the logarithm, we multiply by 2. This becomes 5 log r over 10. 10 parsec, so r in parsec. So this is called the distance modulus. If we know the apparent magnitude of a star and we know its absolute magnitude, we can deduce the distance. And if we know the distance, we can find its absolute magnitude. So on the formula sheet, these two equations are exactly the same, just a different arrangement. Here the order is swapped, and the 10 parsec and the distance have been separated into two different logarithms, and then logarithm of 10 is 1, so you have 5. Anyway, we'll be using this version. On the next part, I will be discussing these last two equations, which contain some very important concepts to us.